I've hit the record button. Okay, well, thank you all for joining me again. This is meeting number 7-ish. I'm not quite sure. I haven't been keeping track. Um, so last time we finished up the drivetrain completely. We added some gussets to the corners, and then I had you all make a belly pan. My belly pan failed for some reason, and I haven't had the time to go back in and rebuild it. So I'll probably do that off stream sometime next week. Or maybe I'll just leave it out because the belly pan isn't terribly important to the overall CAD, or at least for what we're doing because it's trivial to design. Um, Before we get started today, does anyone have any questions about their CAD model or things we want to discuss related to the drivetrain before we move on to a whole new mechanism? I will take that as a no, and that means we can get started with the new stuff. The stuff I'm actually excited about because drivetrains are boring, and now we could get into the cool stuff. So before we get into the CAD today, we need to spend a little bit of time understanding 1678's robot here so we understand what we're going to be building over the next uh, few weeks. There's a bunch of mechanisms on here and it looks really confusing at first, but we're going to kind of go through and break it all down so we can kind of understand what we're grasping at here. So the first and foremost thing is you have this giant elevator. And if you were at the meeting yesterday, I gave a short presentation on elevator design. Don't worry, we're going to go over all of that stuff today, again, specifically related to 1678's robot. But you have here a giant elevator. And specifically, we have what I would probably consider a two-stage elevator. Some people might call this a three-stage elevator, but basically, what you have is you have these blue bars down here at the bottom. These seem to be like, I don't know, how long are these? Let me grab the edge, 44.5 inches long. So you have these, what are called like base bars, I guess. These are the like bottommost bar on the elevator. I wouldn't really consider this a stage because it's kind of anchored into the drivetrain. These blue bars don't move. Then inside of those two blue bars, you have them on either end, you have these silver bars, and these would be what I would consider the first stage of the elevator. These bars sit inside the base of the elevator and roll up and down. These bars are slightly smaller. They're 43.25 inches, so they're 1.25 inches smaller than these longer blue bars. And then additionally, along with this set of bars on the elevator, you have one more second stage. So we would consider these silver bars, when those go up and down, that's what I would consider the first stage of the elevator. And here, this entire mechanism, you can see it's connected on its own set of rollers with its own plates. This is what we would call the second stage, or what I would refer to as the carriage. If you all remember from the presentation yesterday, the final stage of your elevator is typically referred to as a carriage. So going forward, I'm going to refer to these bars as like the base of the elevator. And then you have these silver bars, which is the first stage of the elevator. And then you have this entire setup, which is your carriage or your second stage of the elevator. So that should all be pretty simple. Moving forward, once we have those three stages in, there's a couple other mechanisms that we'll have to design. We'll do the elevator first, and then we'll start designing the other major mechanisms here. One of the major mechanisms they have down here at the bottom is this massive gearbox. So we designed the very simple single-stage gearboxes for the drivetrain. Down here, we have just this behemoth of a gearbox. If you look at this thing has like, I think I counted 12 separate gears in it. It has 4 motors, 4 separate 775s. 12 motors, not including the pinions. So overall, you have 16 motors, or 16 gears, sorry. 12 gears plus 4 pinions. You have 2 pneumatic shifters here. So both of these can shift your gearing because this is a shifting gearbox. And that's all connected to this drum assembly And you can see here they wrap around a string. This would basically be the drum that pulls the string on the elevator. We're not going to worry about designing this quite yet because I haven't fully wrapped my head around how this gearbox works. One of the cool things about what 1678 did is that their elevator not only lifts up game pieces, but it also serves as a climber for their entire robot. And so what they use is they use this mechanism right here, if I could orient myself. So this entire mechanism right here, that's part of their entire climbing assembly. So what they would do when they actually go up and climb, and we'll watch a video again here in a second of them doing this, but when this mechanism folds out, they lower their elevator to lift their entire robot up. And not only that, they have these forks on either side of their robot so they can lift up 3 robots at a time. They can lift up themselves and then a robot on their left and a robot on their right. So if you think about it, this robot, this elevator in general, has to be able to lift upwards of almost 500 pounds of robots. Because every robot can weigh over 160 pounds. So, what is that? 480 pounds of robot that this elevator has to lift up. So basically, you need a really, really torquey gearbox. But if you have a really torquey gearbox, that means your elevator is going to be slow. And so they use shifters to shift between having a very fast gearbox and a very torquey gearbox. The reason they have 2 shifters yet, I have not fully comprehended. This is just going to take me a little bit of re-diagnosis and redesign before we can actually go in and bother building this. So we're not going to worry about that gearbox just yet, but know that it is coming up eventually. The other 2 mechanisms on this robot are this climbing assembly that we looked at briefly a second ago. This entire thing is just bolted to the bottom of their first stage. As you see here, they have a gusset that just straight up mounts it to the bottom of their first stage. So this thing doesn't really move unless the first stage moves. And I don't know if we'll bother designing this. We might, just for the fun of it. But basically, this entire Z-shaped setup, these blue rollers that you see up here, those fold out forwards, and those will actually go onto the 3rd level of the habitat. And then these things right here, these little blue arms with these rollers on the end, those will actually fly out. Those will be released and fly backwards, and those will actually touch the ground. So when the entire first stage moves down, those rollers will push the robot off the ground. And that's how they use their elevators to climb, is since these things come down and will contact the ground, the elevator moving down actually lifts the gearbox or the drivetrain up with it, which is a really cool design. We won't bother modeling this until the very end if we have time, because I don't really care to model their entire climbing assembly. The most important things are the elevator and their intake. The final thing that they have on here is this intake assembly, and this entire assembly is mounted on its own separate stage of the elevator. This is the carriage stage, so as you see, there's these plates on either side that have bearings on them, and that those bearings allow it to run up and down the first stage. Overall, it's a pretty simple intake. You have these kind of complex, really weird-looking plates. Sorry, but they're really not that complicated. You just draw the holes that you need, and then you connect them all together with thick enough metal, and then you remove all the stuff you don't need. It gives you that really cool-looking geometry. Other than that, they have some pneumatics here that can lift out this. I can kind of like open up this jaw, so these rollers will actually come outwards. The rollers are powered by a 775 on a versaplanetary gearbox. You have some smaller pneumatics on the inside, which can actuate this little thing that we'll see in a video. Those grab the hatch panels. The most important part about this entire mechanism is this little assembly over here. And this basically allows the entire assembly to rotate 180 degrees. So you can imagine when this thing is on the ground, this thing will actually flip 180 degrees counterclockwise, so it could face either the front of the robot or the back of the robot. This is what we call a pass-through mechanism, A lot of really high-level teams design pass-through mechanisms because it allows them to cycle faster. They don't need to turn their robot around in order to complete a cycle. They just pass their mechanism from one side of the robot to the other. And so they use a fairly simple gearbox here um, to do that pass through. They have a pretty big gear reduction because for some reason they didn't mount at Versa Planetary on that 775. Don't know why they didn't do that, but they probably had their reasons. So it's like a 3-stage gearbox if you include this giant sprocket they have. So this shouldn't be a very difficult thing to design. We'll probably knock that out within 2 meetings. The first thing I want to do, though, is I want to have you all look at their robot again, so we could kind of get an understanding of what we're going into here. If we go to the Blue Alliance and we go to 1678's 2019 season and we look at this video, this is what I want. Premiere Night Uncensored. Can you all see my screen, by the way? Just making sure here. Okay.
Yeah, we can.
Cool. I didn't know if YouTube would block that out when I went full screen. So let's quickly watch this video and just kind of get an understanding. Pay particular attention to the pass-through mechanism and how the elevator goes up and down. Cool. Let's watch that one more time and I will point out a few things as we go through it. So here you can see that mechanism is facing forward. Once it's lowered all the way to the ground, it can pass through the robot. So that means they have very fast cycle times. The rollers there on the top are used to grab the balls. And then here you could kind of see that secondary mechanism that I talked about where those rollers fell down to the back. And now you'll notice when the robot goes up, they actually do it by lowering the elevator. And lowering the elevator pushes the robot off the ground. And then those rollers on the front allow the robot to move onto the platform while lifting up all of these robots. So, very cool mechanism. We might... I don't know if we'll modify it yet. So, for anyone who was at the meeting yesterday, can you tell me what type of elevator, either continuous or cascading, that Team 1678 is running here?
I think it's a continuous.
It's a what? A continuous? Why do you think it's a continuous elevator?
Because it moves at the same, like the 2 stages.
Sorry, repeat that last part. You were cutting out a little bit for me.
Like the 2 stages like move at the same.
Yes. So you notice here, you'll see this better here in a second when they start cycling power cells. But notice how when the carriage stage moves up, the part with the intake, when that moves up, you'll notice the first stage moves up as well. Notice when they both lift up here, they both move together. So now that the carriage stage is halfway up the first stage is halfway up from the base of the robot. So this is not a continuous elevator. This is actually a cascading elevator. So the cascading elevator means that the gearbox only goes to the first stage, and then the first stage has its own separate cable that then lifts to the second stage. And so the act of moving the first stage moves all the successive stages together at the same time. So just that movement here where you see all of the stages move together at the same time, that's a dead giveaway saying that they use a cascading style rigging. Now, one of the things I did say yesterday was that cascading elevators or cascading style riggings have the disadvantage of having lower torques because every stage gets progressively faster. But obviously, in this situation, you can't have low torque because you literally need to lift 500 pounds worth of robot on your climber. Um, it doesn't matter too much here because they use just an exceptionally beefy gearbox, like with that gearbox and those shifters. It's like they could break bones with that thing. There's so much power in it. Um, but the second thing is that because this entire climbing mechanism is only mounted onto the first stage, you don't get any of those torque losses because your gearbox feeds directly into your first stage. So there's no trade-off between the speed at which your elevator rises versus the amount of torque it has. If they mounted this mechanism to their carriage stage or to a second stage, then they would have to start worrying about that because their carriage stage would move twice as fast, but it would have half the torque. That's all complicated elevator stuff that we don't really need to worry about, but just know that Team 1678 uses a cascading elevator, and we'll look at that when we actually go in and design their rigging. The other thing to keep in mind here is with their pass-through mechanism, the thing has to be at all the way lowered to the ground in order to work. As you notice here, like they have to drop the thing all the way to the bottom before they could pass through. That's why in the CAD model, like in the current configuration where the elevator is fully extended, it obviously can't pass through because it'll hit this top bar. So the entire thing needs to be lowered before this thing could work, just in case any of that confuses you. Okay, so for today, we're only gonna do like maybe 30 minutes worth of CAD. I really just kind of want to get these base bars designed in, and maybe we could start designing in the first stage. Once we have that in the future weeks, then we will design the intake, and then once the entire elevator and intake is designed, then we'll move on to the gearbox and drums, and then we'll look if we want to continue and actually do the climber mechanism. I think this would be fun to design, given that it's very complicated and I don't fully understand how it works. But we'll cross that bridge when we get there. Any questions before we start CADing? Okay, we shall go ahead and get started then. So jumping into our CAD models, if any of you are significantly behind, feel free to just copy my CAD model and like literally make a copy of the entire document and then just get to the point where I'm at. First thing we're going to do is we're going to update our references because for some reason MKCAD updated and the little blue update key annoys me. The second thing we're going to do is we are going to need to go to our main robot assembly, which we created back in like the very first meeting. And I want to go ahead and insert our drivetrain in here. So I want to insert our A-level main drivetrain assembly. Because we are no longer going to be operating inside the drivetrain folder, we are now going to be operating inside a new elevator folder. And in order to put the elevator and the drivetrain together, we're going to do that inside the main robot assembly. So here is our robot at its current configuration. So whenever we start a new major mechanism, we always start by making its own separate folder, and inside that folder we have a dedicated part studio and we have a dedicated main level assembly. So I'm going to start by creating a folder. I'm just going to rename that elevator. Inside that elevator folder, I'm going to create a part studio, and I'm going to rename that part studio as elevator part studio. Just making sure I'm keeping consistent with my naming conventions, yes. And then we're going to create an assembly, and the assembly we're going to name in brackets elevator. It's going to be our A-level assembly, and we're just going to call this main elevator assembly. So this is how I start every new major mechanism. It'll keep everything nice and organized whenever someone else has to go in here and fix issues that are inevitable. So, first things first, we're going to start with the base stage. And the base of their elevator looks like it's a simple 2x1 piece of aluminum tubing. It's 44.5 inches long, and it looks like a 1/16 of an inch thick. Double check here. Yep, 1/16 inch thick. So I'm going to go ahead and head to our part studio, and I'm going to start by creating the first parts, which is going to be a 2x1 piece of tubing. Sixteenth-inch thick. Rename that main sketch for that. I'm going to extrude the entire part by 44.5 inches. And obviously, whenever we make a part, we have to first give it a name. This is going to be elevator part 001. And this is going to be called, I'm just going to call it base rail. You can name it whatever you want, but that's what I'm calling it, base something. We also need to assign the material so we could get a good estimation of our robot weight. 6061 aluminum, like all of the other tubing we buy. And then I'm going to edit the appearance, just make sure it's using the same aluminum color that I used for all the other mechanisms, because these models just look weird when everything is different colors. So, make it realistic. One thing I want to see quickly is I want to add in the holes to the tubing here. But I want to see how much of a difference in terms of weight savings that they actually make on this. The heck is that? Switch Boy? I don't know what they're doing in their models. So this bar is 1.5 pounds, 1.571 pounds, with just kind of fully loaded, not cut out at all. But if we use that tube converter from Chief Delphi, and we use the 1678 style pattern, do two rows, sorry, and we do, what size holes do they use on here? Are we 3/16 of an inch? Yep, 1/16 of an inch. There we go. I'd put in the correct wall thickness. And let's just hit 1 inch face style. We want one row. Doesn't really matter how you do this, but we're gonna go ahead and just convert that tube. I wonder how much it weighs now. Right click, properties. I want to do mass properties. Wow, that did nothing. We only took off 1/10 of a pound worth of weight. So, doing that to all of your bars is questionable at best, I would say. Anyways, moving on. I'm gonna go ahead and start by throwing all the things we just created into their own folder, and I'm gonna just rename that part 1. And we could go ahead and head on over here to the main assembly, and we could go ahead and insert these parts. And we're gonna need 2 of these base rails. Base rail twice. So one thing we have to do here, and this kind of annoys me because it goes against how I like to CAD, which is always CADing with constraining everything properly. But because we're designing in our own separate part studio, away from the drivetrain, we're just gonna have to constrain these together as though there was a drivetrain underneath it. So the way I'm going to do this is I'm just going to look over here at Team 1678's robot, and I could say that these bars are perfectly parallel with each other, but they are 23.5 inches apart. Otherwise, they are perfectly symmetric. I'm just going to start by mating the centers of both of these bars together and offsetting them by 23.5 inches. All right, no problem. Sorry that your laptop's not working. You sound like Aiden.
Excuse you.
Have you decided on which laptop you're gonna get?
No, I'm using my sister's old laptop. I have SolidWorks installed.
Yeah, your sister's gonna be very happy that you're using SolidWorks on her laptop. Hmm.
Oh, she doesn't care. She has a Mac now, and she can text on it. That's her favorite part. So
Well, if it works, it works. Base Rails. We shall hopefully start getting into the SolidWorks soon. Oh, I mentioned this last time. I'm gonna mention it here again. I'm not gonna have any meetings next week because I have all of my George Mason finals next week. So as soon as finals are over, we can start getting into more cool stuff. When does school end for all of y'all?
like June something.
Or
Yikes.
I think second.
What was that, Tanuj?
I think second week of June.
And you guys have a whole month extra of school compared to us. A month and a week. I was
Do
hoping
you
that.
think it would be helpful to change our mouse controls to SolidWorks now so we could get used to it, or no?
Oh, yes.
Okay, because right now I'm using AutoCAD controls.
Using
Is that
AutoCAD
something you
controls? You're
can
not using the default Onshape controls?
I know,
What are you
I know.
doing? The default Onshape controls are amazing. Are you kidding me? You could do everything with a single mouse. Oh, I'm.
I like my shift key.
Why?
Bro, you use shift? Also, why are the holes on the robot like off center to the side
I was looking at that and I think it is because.
of the roller?
Yeah, exactly. Because these bearings get in the way, and I just remembered that that was an issue on the last elevator I designed. Um, so we might need to actually go in and fix that. I wonder if there's something we could do in the tube converter to adjust that.
You can change if it's centered on the tube or not.
Offset from end. Um, doesn't really. Oh, that offsets it that way. I don't want to offset it that way though. 2.5. Yeah. I'm actually just going to delete the tube converter and do that manually. Because tube converter does not have that feature. So they're using 16th inch holes, but they're offset from the left by a quarter of an inch. Left, right, doesn't matter. So I'm gonna start by drawing a construction sketch along the entire length. Actually, no, I'm not gonna do that. Waste. I'm just gonna start by drawing a circle of 3/16 inch diameter. I'm gonna mate it a quarter of an inch from the left and a quarter inch from the top. Name this 1 inch side holes. And I need to pattern that. Almost forgot. Pattern one in that direction, like 90 in that direction, and we want them to be offset by half an inch. Maybe 90 was excessive. No, 90 was actually almost perfect. Holy crap, 89. Man, I'm a genius. Okay, finish that. Extrude that sketch. Remove all. Okay, and then I'm
What was
just
your distance between the holes?
half an inch.
Right.
And then I'm just gonna do the same thing on the left side, or on the 2-inch side. But just kind of make it standard. Sorry, 3/16. That should be. Do an inch, no. Half inch from the left. A 1/4 inch from the top. And then we're gonna pattern pattern 2 inch to the left, and 989. They're gonna be shortened by half an inch. Okay, I can name this 2-inch side holes. Extrude that sketch, remove all. Okay. Okay, so there's our base sketch rail. And then on the elevator, we just want to make sure that we have everything oriented correctly. So you want the holes to be on the outside. I just need to change my mates. Works. I'm just going to rotate you 180 degrees, and remate these both together with a fasten mate in the middle. It's just going to be offset. I really hate doing this because this isn't how good CAD is done technically, but until Onshape allows you to mate to other assemblies without having to insert those assemblies, this is how we have to do it. If they could do like in context assembly mates, just like how they do in context part studios, that would be so cool. Base rails. Okay, cool. So we have that. Moving onwards. What else do we need? So on the bottom, so there's a bunch of giant holes along here. I don't know what those do. I don't know what they're for. It's not obvious to me. They have no mounting holes. They don't go all the way through. The only thing I could think of them being for is if you need to access cabling on the inside, but there is no cabling being ran on the inside. All the cabling is being ran on the outside. I'm going to be completely honest, I don't know. If we need them, we'll add them in later. But right now, they really have this gusset going through this piece of polycarb. Shaking my head, 1678. Not going to bother with this because this entire assembly is for climbing rails. The only real things we need, I guess we could go ahead and design this, which is going to be just like a support in a sense, to prevent like lateral loads on the elevator. And then it's just a bunch of gussets to connect everything. So let's go ahead and add that. So that is a bar that is 23.945 inches. Why that specific, I don't know. Didn't even flatten it on the bottom. That kind of annoys me. I'm going to do it my own way. So first I'm going to throw all of these into a folder. Hide that base rail now that we've made it. Now I'm going to make another rail. So we need a 1-inch bar, 1x1 aluminum. that is a 1/16 of an inch thick. I'm gonna go ahead and make it 24 inches because I'm gonna be a rebel. Start rectangle 1 by 1. Use the offset tool. Offset inwards by 1/16 of an inch. Rename the sketch because renaming your sketches is always helpful. Extrude it by 24 inches. Obviously, we have to go through and start naming our part. I'm gonna call this diagonal brace. No, diagonal support. It's not really a brace, it's a support. Throw that into its own folder. Edit the appearance. Appearance is already good. Edit the material to make sure it's 6061, so whenever someone pulls this up, they know that this is 6061 aluminum. And then we could use the tube converter on this to just add our holes in everywhere. Yeah, that looks good. So on 1678's robot, they don't really... They didn't flatten it down here, which doesn't really matter. For some reason, they have these cutouts up here. Oh, I see. So they do this weird kind of cutout up here because I assume when this thing comes rolling down, the bearings might collide. But that is hard to tell because their assembly has no movement in it. So whatever, we might just have to go back in and fix it. I'm not going to bother modeling this in right now. Actually, maybe I will. Try and think of how deep of a cut is that. That's a 45-degree angle. Yeah, I'm not going to model that in right now. Oh wait, they do have some mate features in here, and I've never tried getting these working. Oh my god, it does move. Holy jeez. How long have I been looking at this assembly and never realized that this entire thing moves? Yo, and it actually has a cascading style mate to it. That's sick. Wow. They actually went over the top, or not over the top, but they did better than I anticipated them to do on this, considering that I did not realize they even had mates working in this assembly. So this is cool. Wow, I had no idea. Look at that. Now everything's all nice and compact. You can actually get the mechanism to flip over itself in the CAD model. That's sick. This is the type of the level of mate fidelity that I want in our models. So it's so cool when you could get, you know, when someone could go into your CAD model and actually play around with some of these mates and see how everything works. You really get an idea for how the cascading rigging works here, because like I cannot lift the carriage to the top of the first stage without lifting the first stage to the top of the base stage here. With a continuous elevator, you would be able to do that. But on a cascading style, you cannot do that. And they even mated that incorrectly, which is very impressive. Good work, 1678. Anyway, I got distracted there. What was I looking at? I was looking at this guy. When you lift this guy up, you have a bit of interference there, their CAD model, which is not optimal. But the main thing is you do not want your bearings here to hit. And they have so much clearance on that. Actually, no, they Okay, whatever. You know what I'm gonna do? I'm gonna do a happy little compromise. I'm gonna take this part and I'm just gonna change the extrusion to 23 inches. You know what? That is gonna be how we deal with that. We don't even need this part right now. I'm not, screw it. I'm not gonna words. I'm not gonna bother modeling that in because that is a support structure. We will model it in at the end when we know how the bearings and everything else will affect it. So we'll just leave it for right now, but I'm not gonna bother bringing it into the CAD. So yeah, moving on. What is the next major part of our elevator? I'm not gonna bother with the gussets. Gussets you can do at the very end because those are trivial. Next thing I'm gonna do is use this, do the first stage. And so the first stage is another set of 2x1 tubing. That is 23.25 inches long, 16th inch wall. No holes on it this time. If the actual robot has holes on it. Look like it. No, it doesn't. Okay. So we're just gonna go back into the Bart Studio, create another sketch, and then just do 2x1 tubing again. Sixteenth inch wall. 43.25 inches extrusion. Continues just editing my extrusion for some reason. So first thing I'm gonna do is I'm gonna rename this elevator part 3, and I'm gonna call this first stage rail. I'm gonna edit its appearance so it's not this ugly blue color, and assign its material to be 6061. And I'm gonna go into my assembly and I'm gonna drop in 2 of those. Actually, what I'm gonna do here is, now that I'm thinking about it, I should probably make an entirely separate assembly for the first stage. And so I could, have an assembly for the carriage stage, put the carriage stage in the first stage assembly, and then put the first stage assembly in the main elevator assembly. And that will just keep everything nice and organized, and I don't have a bunch of very confusing movement mates and whatnot. So I'm actually going to go over here, create a new assembly, and I'm going to create a assembly 1 level down from my main elevator assembly. So I'm going to create a B level assembly. And I'm just going to rename it first stage. And in here, I'm going to, not bring in everything, I'm just going to bring in 2 first stage rails. I could just let those chill in here for right now. So what do we need on our first stage? Well, unlike the carriage stage, which is only constrained from the bottom, the first stage is actually constrained from both the bottom and the top. And so up here on the first stage, they have a piece of 2x1 that basically just serves as a very simple brace across the entire thing, has a bunch of holes cut out, and then they have a small gusset there that braces between the two. And then on the bottom, they have a large piece of, I'm looking at the wrong place here, a large piece of 2x2 aluminum. And that 2x2 serves as not only the brace for the bottom of the first stage, but it also serves as an anchor point between, for all of the climbing stuff. So we're going to go ahead and model both of those parts as well. So after I throw part 3 in a folder, I'm going to, again, create a new part. I can sketch it here. I'm going to create first that top bar up here. This is what I'm going to be creating. So it's just a simple piece of 2x1 that's a 1/16 of an inch thick, and it is 21 inches long. So 2x1 use the offset tool. Offset by 1/16 of an inch. Rename my sketch. Keep track of stuff. Extrude by 21 inches. Then I'm going to use the tube converter and do a 2-row style. That's what 1678 does. Rename that elevator part 4, and I'm going to rename it first stage top brace, and obviously change its appearance. Appearance is already up there. We go. And then change its material. I'm going to go ahead and drop that into my first stage assembly. And I'm going to kind of just arrange it to how it eventually is going to look. Yeah, basically like that. I'll bother with the mates later. So finally, I'm gonna throw those into a folder, and I'm just gonna create that last part for today, which is gonna be that. Sorry, wrong tab. It's gonna be that 2x2 brace at the bottom of the first stage, near the bottom of the first stage. Sorry, it's not actually at the very bottom. There's about a 1 3/4 inch, exactly 1 3/4 inch of clearance at the bottom. Reason for that, I'm not sure yet, but I'm sure it will become clear as we move. What's the purpose of it? Interesting. No idea. So back into the part studio, and make one more part. This, instead of being a 2x1, is going to be a 2x2. Offset 1/16 of an inch inwards. I'm going to extrude it again. I assume it's 21 inches, just like the top bar. I should probably double check that, though it really shouldn't be different. Yep, 21 inches. As always, we start by renaming the part. It's going to be part 5, first stage, bottom brace. Edit its appearance to be the same as all the other aluminums. Edit its material so it is 61. And then it uses a pretty standard 2-row. God, I can't speak. Just use the tube converter. Basically what I'm trying to say here. And then throw those in a folder. And then I can insert that to now I'm just going to go ahead and kind of tack all of these together with some very simple mates. Should probably actually use the correct mate here. So first off, I'm going to fasten the bottom brace to the bottom of one of the side rails. But you want to make sure you offset it by the amount that is offset on the actual CAD model, which is going to be negative 1.75 inches. Because that's how high off the bottom of the first stage this bar is. Yep, 1.75. Just going to make sure that is done clearly for ends. I'm just going to rename this bottom brace. And 0.75 inches down. And then I'm going to do that again for the top here. I'm just going to fasten this to the top left corner of one of the braces. So you should be left with something that looks like this. Very simple. It's okay to use fasten mates here because if we think about it, you're going to have gusset plates kind of connect everything together. And that is basically a fasten mate because you don't have any degrees of freedom when you plate two things together. Use rivets on anything. The only other thing I'm going to do here is I'm going to go ahead and drop the first stage assembly into my main assembly. So I could just kind of keep everything together. And get an idea for how they'll eventually look. And then I'm also going to very quickly insert my main elevator assembly into my main robot assembly. Because why not? Might as well get a look at the entire robot as it slowly comes together. And if we look at 1678, their elevator is mounted 9 inches from the back of the back rail. So I'm just going to do a simple fasten mate from this corner, offset it -9 inches in the X direction. They rename that elevator. And just kind of get them aligned. We'll mate these at another point in time. Okay, cool. That's all I'm gonna do today, I think, because I have a bunch of other stuff that I still need to get done before finals start here at George Mason. So I need to get back to work on that stuff. Do any of you have any questions about what we discussed today or did today? Everything we did was, super basic. It was literally just a bunch of tube extrusions. So, day one CAD stuff. Cool. So I think next meeting, what we will probably do is I will, I think we'll go ahead and, I don't know if I want to do like the actual movement of the rails first. I didn't even use that. I guess that would probably be best, is actually start modeling in the bearings and mating the elevator so it actually moves properly before we start getting into the whole intake. Have the elevator fully finished, and then we can go into the intake and the gearbox potentially. Wow, I didn't even notice they have 2 limelights here. One, I noticed the upside down one there, but I never noticed this guy in here. That's interesting. That is a big aluminum plate. Wow, I never noticed that either. What is the purpose of that? Interesting. A lot of cool stuff that we need breakdown in here. Okay, so final questions before we end for today.
If you're not coming next week, make sure that you remember to tell the mechanical captains that we're not doing CAD.
Yes, I already told them today that they need to figure out what they're going to do for the next meeting.